So let's look at a couple more examples together. I'm going to be a little bit quicker on the details on this than on our first example, because it's very easy in some of these examples to get lost in the algebra and the sort of the particulars of the manipulations that you need to establish the inductive case is true. And so I want you to try as much as possible to pay attention to the form, the logical form in which we're writing these things out, and I'll try and not get bogged down in those details too much. But of course, you can always review this video later and work it out for yourself if you like. So what I'd like to do is together look at numbers 1 and 3 from this list. So the first question is the statement that the sum of the first n perfect squares, so 1 squared plus 2 squared up to n squared, can be written as n times n plus 1 times 2n plus 1 all divided by 6. So it feels an awful lot like the first example that we did. It's just perfect squares instead of all the natural numbers. And the second example we'll do together is this one right here, which is that n factorial is greater than or equal to 4 to the n for all n's greater than or equal to 9. So one of the differences with this one is that this is not a statement that we're claiming is true for all natural numbers n, but we're claiming it's true for all n beginning from a certain point. So in this example, we're beginning from 9. So that statement needs to be true for n equals 9, 10, 11, 12, 13, and so forth. But we do not have to show that it's true for n equals 6 or 2 or 1, right? So just a little bit of a subtle difference. And by the way, a statement like number 3 is something that you might use in a calculus course, for example, if you're trying to quantify the convergence of an infinite series that has a factorial in it, and you can compare that series to a different series which has a 4 to the n in it. We can make what's called a direct comparison if we have a statement similar to this one. It's a bit like saying that in the long run, as we go out towards infinity, eventually the factorials grow faster than the powers of 4 do. So the n factorials are going to overtake the 4 to the n's eventually. And in this example, we're showing that it happens as soon as we pass n equals 9, and from there on out, the factorials are always greater. So to establish this summation formula for the first n perfect squares, we again want to do this by induction. And since so much of the work happens in the inductive step, I'm going to do the inductive step first for both this proof and the next proof. Again, you could choose to work on it in whichever order, but since the base case is usually so quick and dirty, I want to spend the most of our time talking about how to make this inductive case. So in the inductive case, we first make the inductive hypothesis. Assume that the statement is true for an arbitrary natural number k. So we assume that the sum of the first k perfect squares is k times k plus 1 times 2k plus 1 divided by 6. And then the thing that we're going to try to show is that the statement must then be true for k plus 1. So I evaluate this with k plus 1s in place of the n's, and I say that the sum of the first k plus 1 perfect squares is k plus 1 times k plus 1 plus 1, so that would be k plus 2, times twice k plus 1, adding in some parentheses there to be extra careful, twice the quantity k plus 1, all divided by 6. And so that's the thing that I'm trying to prove, and I am going to do a little bit of simplification on the right-hand side here, just to make it a little bit more obvious for me to know when I've gotten to where I'm going. So k plus 1 times k plus 2 times, distribute out this quantity here, I get 2k plus 3. So what I'm trying to show is that the sum of the first k plus 1 natural numbers is k plus 1 times k plus 2 times 2k plus 3, all divided by 6. So just as with the previous example, the key to an inductive proof is discovering the inductive hypothesis from within the inductive case we're trying to prove. Here we're summing up the first k plus 1 perfect squares. But we cannot sum the first k plus 1 perfect squares unless we have first summed up the first k perfect squares. So realizing that there is a k squared here on the way to k plus 1 squared, that is the key insight, because that's what gives us the ability to plug in our inductive hypothesis. Because we have assumed that we know that the sum of the first k perfect squares has this particular form, k plus 1, 2k plus 1, all divided by 6. And that assumption is what allows us to replace that sum of the first k perfect squares with k plus 1, 2k plus 1 over 6. And so the sum of the first k plus 1 perfect squares is k plus 1, 2k plus 1 over 6, plus my final term, k plus 1, the quantity squared. And now we know what we need to do. Whatever algebra is necessary to demonstrate that this expression is equal to this expression. And so just like before, I'm just going to try to do this as elegantly as possible, for whatever that means, and factor out a k plus 1 from both of these terms. That's going to leave me with a k times a 2k plus 1 over 6 from the first term, and it'll leave me with an extra k plus 1 factor from the second term. And then I'll find common denominators on the inside for this rational expression, 6k plus 6 over 6. Add across, 2k squared plus k plus 6k plus 6, all divided by 6. Now I reach into my Algebra 2 class from high school, and I figure out, well, how can I factor this polynomial that's up here on the top, 2k squared plus k plus 6k plus 6? I can't quite factor it by grouping, but I can if I write the 7k's that are here in the middle as a 4k and a 3k, because then the first pair of terms has a common factor of k plus 2, the second pair of terms has a common factor of k plus 2, and I can factor by grouping, k plus 2 times 2k plus k plus 2 times 3. And so what I have is k plus 2 times 2k plus 3. And that's what we claimed that the numerator was going to be, all divided by 6 with a k plus 1 out in the front. So if you don't believe me on that step, there are many different ways that you could go about trying to factor that numerator. Factoring quadratics with a leading coefficient not equal to 1, something we don't get enough practice doing, apparently. But that would be how the algebra that we would need to establish this. So as far as the napkin version of the inductive step for this proof, this is what it would look like. Right? In order to add up the first k plus 1 perfect squares, we first add up the first k perfect squares, and we know that we've assumed a form in our inductive hypothesis for what the sum of the first k perfect squares must be. And once we've applied that inductive hypothesis, we then just have to do whatever nasty algebra that we need to do to show that indeed the right-hand side of this expression is the right-hand side that we would have expected for the k plus first proposition of my list of propositions. So let's just actually write this piece up. In a proof, we'll say, we'll proceed by induction on n. So this is what clues the reader to the fact that we're going to now make an argument that includes a base case and it includes this inductive case, and that n is the variable that we're using induction on, so that we can show that it's true for all natural numbers n. And since the set of natural numbers begins with 1, which is actually a little bit of a controversial statement among some mathematical crowds, I'm going to kind of leave that off to the side. I have very strong feelings that natural numbers should start at 1. So if 1 is the first natural number, which I'm going to say it is, then n equals 1 should be our base case. So let's check that base case also before we present our inductive step. And this is the very concrete one, where again we look at the left-hand side and say this is supposed to be the sum of the first n perfect squares. What's the sum of the first 1 perfect square? Well, it's just 1 squared, which is equal to 1. And then on the right-hand side, we're supposed to have 1 times 1 plus 1 times twice 1 plus 1, all divided by 6. That's 1 times 2 times 3, all divided by 6. That's 6 over 6. That's 1. And so in our base case, we have a left-hand side and a right-hand side are both equal to 1. So we've proven our base case. Again, very concrete, very specific, ends up giving me just a number. Now for the inductive step. We make very explicit to the reader when we make our induction hypothesis. We'll say, let's assume that my statement is true when n is equal to some arbitrary k. So assume that 1 squared plus 2 squared up to k squared is equal to k times k plus 1 times 2k plus 1 over 6. Then we would like to show that the sum of the first k plus 1 perfect squares has this form. And now again, this sort of answers the question we talked about just before this proof, which is when you work on both sides of an equation, what happens when you then try to present that in a proof? Usually in the proof, we work from one side to the other. So I have all of the napkin work to guide me, but when I present it in my proof, I'm going to start from the left-hand side and then just go one step at a time until I've arrived at, magically, precisely the right-hand side that we needed to establish our claim. So the sum of the first k plus 1 perfect squares is the sum of the first k perfect squares plus an additional k plus 1 squared on the end. And now, we'll tell the reader that we're applying the inductive hypothesis. By our inductive assumption, 1 squared plus 2 squared up to k squared is k times k plus 1 times 2k plus 1 over 6. And then I need to add that to k plus 1 squared. Then I do the algebra that's necessary to get me exactly to where I was supposed to have been going in the first place. And so when we present the proof in writing, it looks like we've just gone from the left-hand side to the right-hand side, when in reality, over here on our napkin, we were doing a little bit of both sides work to make sure that we could get from one side to the other. We met in the middle a little bit on our napkin, but then in the finished proof, we go from left to right. And then we say this sentence at the end, by the principle of mathematical induction, our statement holds for all natural numbers n. So in our next example, we want to prove this inequality over here, that n factorial is greater than or equal to 4 to the power n for all natural numbers n beginning from n equals 9. Right? So this is a little bit different because we're in a different starting point for our natural numbers compared to our previous example. But the process of writing an inductive proof remains the same. I'm again going to start by thinking about what is the inductive step. What is the inductive case going to look like? So we'll write out our inductive hypothesis. This is the hypothesis that my statement is true for an arbitrary value of k, and then we need to prove that the statement is true for k plus 1. So we assume that k is some arbitrary natural number and k factorial is greater than or equal to 4 to the k. And we must then prove that k plus 1 factorial is greater than or equal to 4 to the k plus 1. So this is, again, all work that I'm going to do just on a napkin over here on the side for right now. Okay, so as usual, the trick in discovering how to write up an inductive step is sort of surfacing the inductive hypothesis from within the inductive step that we're trying to prove. We are trying to prove something about k plus 1 factorial, but we only know something about k factorial. And so knowing how those two are related to one another is 100% of the key in figuring out how to use the inductive hypothesis. What does k plus 1 factorial mean? It's the product, it's not the sum this time, it's the product of the first k plus 1 natural numbers, 1 times 2 times 3 times 4, all the way up to k plus 1. So I'll just write that out. This is my cocktail napkin. I can write whatever I want, right? 1 times 2 times 3, all the way up to k plus 1. But as with before, we cannot multiply the first k plus 1 natural numbers without first multiplying the first k natural numbers. And when I've multiplied the first k natural numbers, what have I computed but k factorial? And I know something about k factorial when I take the inductive hypothesis. So once again, that is the key to doing this, right? Multiplying the first k natural numbers gives me k factorial, and my inductive hypothesis has told me that I can assert something about k factorial. I can assert that k factorial is greater than or equal to 4 to the k. And so k plus 1 factorial is equal to k factorial times k plus 1. And by our assumption, that will then be greater than or equal to 4 to the k times k plus 1. I do want to pause here for just a moment because we're working with inequalities instead of equalities. And that always involves a little bit of extra care as well. We should make sure, for example, that knowing that k factorial is greater than or equal to 4 to the k will guarantee that k factorial times something is greater than or equal to 4 to the k times something. Because that's not always true for inequalities. Sometimes an inequality will end up switching itself around if I multiply or divide both sides by a certain quantity. What is the rule of thumb that we tend to use for inequalities that tells us when the sense of an inequality should be preserved or when the sense of an inequality should be reversed? Usually when we learn how to solve inequalities, the thing that we remember the most is that inequality is reversed when I divide both sides by a negative number. Right? And that's true. I mean, that's definitely true. But it's a specific instance of a larger phenomenon that we may end up getting a chance to talk about more when we talk about functions in our next chapter. And the more general phenomenon is that an inequality reverses anytime we apply a decreasing function to both sides. Right? And the function, for example, f of x equals x divided by negative 2. That's a decreasing function, right? If you just look at a graph, its graph goes down as we go from left to right. It's a decreasing function. If you're taking calculus, which presumably you are this semester or have taken calculus, you'll also know that a decreasing function can be characterized by its derivative being negative, right? And so those functions, when I apply them to both sides of an inequality, actually by definition of decreasing, will reverse the sense of that inequality. So, knowing that this inequality guarantees this one just requires us to know that I'm multiplying this inequality on both sides by k plus 1, and k plus 1 happens to be a positive natural number, right? K plus 1 is positive. So when I multiply both sides of this equation by a positive number, I'm going to preserve the sense of that inequality because f of x equals k plus 1 times x will be an increasing function. Its graph will go up from left to right because k plus 1 is a positive number, and that's the slope of the line. Okay, so enough about that for right now. We'll get a chance to probably talk about that some more in chapter 3. So I can replace k factorial by 4 to the k by my inductive hypothesis by placing a greater than or equal to sign in between. Now I just need to know, how do I get the rest of the way? How do I get to 4 to the k plus 1? And here's another place where I'm going to do just a little bit of work on the right-hand side of my inequality. 4 to the k plus 1 is nothing more than 4 to the k times 4 to the power 1. So I'm going to just peel off one of those factors of 4 so that I can find a 4 to the k sitting right there. And it kind of shows me, in order to get from here to there, I need to explain how I know that k plus 1 is greater than or equal to 4. Well, how do I know that k plus 1 is greater than or equal to 4? I know that because k is a natural number which cannot be any less than 9, because 9 is where the domain of quantification for all of the n's for which we need this thing to be true begins. And so over here off to the side, we're going to convince ourselves that because we know for sure that k is greater than or equal to 9, k plus 1 is for sure going to be greater than or equal to 10. And because it's greater than or equal to 10, it must in particular also be greater than or equal to 4, because 10 is greater than or equal to 4. Right? And so it is a valid thing to do to replace k plus 1 by 4 by placing a greater than or equal to sign right here. And now that I've done that, 4 to the k times 4 is equal to 4 to the k plus 1. And when I read this thing from left to right, I've proven that k plus 1 factorial is equal to something, which is equal to something, which is greater than or equal to something, which is greater than or equal to something, which is equal to 4 to the k plus 1. So it's a bit like saying wherever k plus 1 is on the number line, the next thing in my logic here is at the same spot on the number line. The thing after that is in the same spot on the number line, but then the thing after that is somewhere potentially to the left on the number line, right? Greater than or equal to. And then again, we have greater than or equal to, so we might move a little bit further to the left as well. But then that's equal to 4 to the k plus 1. So 4 to the k plus 1 is over here, k plus 1 factorial is over here, so k plus 1 factorial is greater. I think my hands are in the wrong order from reading from left to right, but you get the idea, right? When you're working with an inequality from left to right, you need to always make sure that whatever inequality symbols that you use along the way are always pointing in the same direction. We know that we're starting somewhere higher on the number line, and as we go along, we're only taking steps that could take us further to the left. Right? This could be smaller, but it could be equal. This could be smaller, but it could be equal. If at some point we try to take a step back in the other direction, we have completely lost the tune. Right? We don't know how big that step backwards is. Maybe it takes us too far. Right? But anytime we're writing an inequality from left to right, as long as we're always making moves that are only in the same direction, we will get a valid compound inequality at the end of the day. This process, by the way, of working with inequalities in order to establish that they are true, this is probably one of the most difficult skills that students face in their Introduction to Analysis course, the Math 401 course that you're required to take as a math major. And so the more practice that you get in this course working with inequalities and making these kinds of arguments, the more ready that you're going to be, because a lot of arguments in real analysis, which is the topic where we justify not only what is calculus, but why does calculus work and what are the properties of the real numbers that make calculus possible, rely very heavily on these kinds of arguments about inequalities. So the more practice that you get now, the better. Let's check the base case. We did a lot of hard thinking to figure out this inductive case, so this is like the cherry on the sundae. Let's check the base case. And here, the base case, because my first domino in the line is the domino for n equals 9, we just have to plug in n equals 9 into this inequality and figure out if it is indeed a true statement. Is it true that 9 factorial is greater than or equal to 4 to the power 9? And this is a place where you do actually need to pull out a calculator or a phone or some kind of technology, right? 9 factorial is 362,880. 4 to the power 9 is 262,144. And sure enough, the former is greater than or equal to the latter. And that establishes the base case. And so when you write up the proof, and I won't do it on the screen this time, you will say, we'll proceed by induction on n. First, checking the base case. When n is equal to 9, 9 factorial is equal to 362,880. Which is greater than or equal to 262,114, which is equal to 4 to the power 9. Base case, checked. Now, we assume that for an arbitrary k greater than or equal to 9, we know that k factorial is greater than or equal to 4 to the k. We must prove that k plus 1 factorial is greater than or equal to 4 to the k plus 1. But k plus 1 factorial is equal to k factorial times k plus 1. And by our inductive hypothesis, k factorial is greater than or equal to 4 to the k. And so this expression is greater than or equal to 4 to the k times k plus 1. And since k is greater than or equal to 9 by assumption, k plus 1 is greater than or equal to 10, and hence greater than or equal to 4. And so we can write that this expression is greater than or equal to 4 to the k times 4, which is equal to 4 to the k plus 1, which is the right-hand side that we asserted we would need to prove true for the inductive step. Therefore, by the principle of mathematical induction, we have proven that this inequality holds for all values of n greater than or equal to 9.